So in natural sampling, in frequency domain, the envelope is that of a sinc function. As per our analysis, the overall spectrum goes to 0 at f equal to plus minus 3 fs, plus minus 6 fs, and this goes on. Okay. So if at all we need to draw the envelope of the sinc function, so that function should also have its 0 crossing at plus minus 3 fs, plus minus 6 fs. So such a function, I think, should be d of sine of pi f upon 3 fs upon pi f upon 3 fs. Or this should be d sinc of, if at all we are using the terminology that sinc of x is sine pi x upon pi x, then it should be sinc of f upon 3 fs. So you will observe that if at all your f is plus minus 3 fs, plus minus 6 fs, this goes on, the sine function becomes a even or odd multiple of pi. So once this becomes an even or odd multiple of pi, this goes to 0. So this function will have 0 crossings at this point. Instead, what we wrote that day was that this envelope is like the sine of pi n f upon pi n f. Okay, which I feel that is not right, because you cannot get, there is no role of n here because you are drawing envelope. So n has nothing to do. So this was, I think, this is a mistake in the textbook. And if at all, I have not checked because there was some errata which was printed when the book was out. It is given on the web page of the author. So maybe he has mentioned it there. But without checking, I just told you what I feel is right. So it should be like this, d of sine. If any one of you has gone through it and you also observed it, you can unmute and say that yes, or if at all I am incorrect, then you can point it out. Second thing which I wanted to say, so this was the first thing which I wanted to say about the last lecture. Second thing is, in general, or you can say that truly that it happens, if at all there are two complex numbers, A and B, if I try to calculate the magnitude, it won't be equal to magnitude of A plus magnitude of B. This should be, I think this you all must be knowing. But we used the property here. Okay, let me show you that where we used this property. We used it here. We said that if at all WSF was this thing multiplied by this, we said that the magnitude of this will be summation of the magnitudes. So this should give some sort of a problem to you, a trouble to you, that how is this happening? This is the case because absolute value of A plus B cannot be equal to absolute value of A plus absolute value of B. Let us check this. If at all, for those who cannot understand it in the first course, suppose we have considered two numbers which are complex. Okay, now you check what is the absolute value of A1 plus B1 plus J times A2 plus B2. Okay. This is simply under root of A1 plus B1 square plus A2 plus B2 square. Okay. And if you check the individual values, so mod of A is under root of A1 square plus A2 square. Mod B is under root of B1 square plus B2 square. Okay. So you can clearly see that the left hand side, this cannot be equal to the addition of these two. But what is happening in our case? Suppose we assume that, let me write it down, that WSF is, if WSF is equal to, suppose this is equal to summation n is equal to minus infinity to infinity, C of n, that is d sine of n pi t upon n pi t W of F minus Fs. And so this was the original spectrum which we had. Now we took the absolute value and we wrote down that this is simply summation n is equal to minus infinity to infinity. D is already a positive number. It is basically a real number which is positive because t is 1 by 3. This is the duty cycle. This is anyways positive, otherwise it would have been negative, so we would place an absolute value operator here, but we do not place it because this is positive. Then we put an operator here, n pi t upon n pi t, and then we put like this. Okay, and this. Now you will think that how does this happen, because WSF is now, until now we have not said what is this. See, this can be a complex number as well. This can be complex. We know from the Fourier transform theory that in general Fourier transform should be complex. Although there are signals for which Fourier transform is real, suppose like pulse. The Fourier transform is a sinc function. Okay. So if this is complex, then how are we doing this? So this is a question which should come to your mind. Now the answer is simple. Let me show it to you. See, if you draw the shape of this, if you consider this condition, for a particular f, if at all my sampling rate is greater than twice of p, okay. So we observe that for a particular range of f, only one of this subterms in the summation exists. Okay. So this you can see from here that this is the term. So you will observe that only if at all I am considering f lying between minus b to b, only one of the term out of this summation is there. It exists, rest all are zero. So with this phenomenon, you can simply say that this property holds. Why? Because if I take the absolute value of this if I take the absolute value of WSF in mod f less than b, so we will get there is only one term, that is d sine of n pi t upon n pi t, this W of f. Okay, so there is only one term. Now if I take the absolute value of this, okay, so you know that if at all I take the absolute value of the product, so it can be written as the absolute value of each of the terms. Okay, this is the fact. That is, if I can write this is equal to, see, d is already positive, so d comes out. If sign, this is a real term, so you can simply, you need to take care of the negative sign. So for that you place an absolute operator here, and then what is remaining is W. So because of this, this is valid. The above expression which we have written is valid. So for those who while studying the notes are quite cautious, so they should have this question in mind. If at all they were able to solve it, they were able to understand it themselves, that's very, very good. But I felt it is a duty that I should discuss this. Okay. Last time, basically I also observed it last time, then I thought that let me discuss it with you all. So because of this happens. Now an associated thing in the sampling theorem, okay, an associated solution, right? An associated. Okay. So an associated thing in sampling theorem. There also there is a trouble. Okay. Why there is a trouble? Because sampling theorem says that you will have shifted replicas of original spectrum. It simply says this. It doesn't say that this will be the property of the magnitude spectrum. Okay. So it says that, let us say, if at all you have some W of f and there is a signal which is W of t, you sample WT at some rate. So let us say if I denote sample WT in octane WST, so you will get that WSF was simply the shifted replicas of the original spectrum, where Fs is the sampling rate. Okay. So while studying that, we saw that if at all your sampling rate is greater than the maximum bandwidth of or the maximum frequency content of W of F, you will get back the original signal by low pass filtering. In the case of ideal filtering, ideal recovery, you use the sinc function. That is the ideal low pass filter. Okay. But we never said that this is also correct. We generally draw this. We say that we never said this. Well, this is not the outcome of the sampling theorem. Sampling theorem says this. So while studying it, what we did was we said that let us assume that there is some signal which is band limited to maybe minus B hertz. Okay. We said that after sampling, let us say the spectrum is like this. Okay. We said this. And in the case of aliasing, what we studied was this, that if at all there is a signal like this and an aliasing happens, so in this region, which is holding frequency by 2, this will have a different sort of a shape. So simply added both of the spectrums. So this is also a point of confusion. See, sampling theorem, because they are in general complex. So if I'm adding for a particular frequency, if I'm adding several complex numbers, so the absolute value cannot be the sum of their individual absolute values. This can be clearly seen from the small example which I have taken here. This you can check. Okay. So you will find in textbooks, you will find in textbooks in footnote that a particular example is taken. A particular example where this is valid. This is valid is taken for illustration. Okay. For illustration. So this you will find in Couch's book also. You will find this in maybe Couch's book, Tu's book, and in other textbooks as well. Lathi also, I think. There I have not checked, but Lathi must have also written it. He can also sometimes write it, but you should know that this is what we are really doing. Okay. There are two things which I wanted to say about this are over. Here, in the case of instantaneous sampling, the third thing which I now want to say in the case of instantaneous sampling, I think in the last class we were rushing. I was basically rushing in order to complete this. So this I didn't discuss that. Let us say you have, impulse train in frequency domain. Impulse train in the frequency domain. Okay. So let us say that you have impulse train in the frequency domain. What I mean that let us say you have this f-axis and I am drawing this one impulse, it is 0, then this impulse comes, then again this impulse, and this goes on in both the sides. Okay. This is 0, this is f of s, this is 2 of f of s, 3 of f of s, minus f of s, minus 2 of f of s, and this goes on the left side as well. And suppose the magnitude, you can say, or the power in the impulse will be 1 by Ts. Suppose this is the amplitude, this is the scaling. So you say that this is simply 1 upon T of S summation delta of F minus K of Fs, where K lies from minus infinity to infinity. Suppose this is a period. So this is a periodic signal. This is a periodic signal in frequency domain. So we used one result where we wrote this signal as a Fourier series in frequency. Okay. This was interesting. So we wrote the Fourier series of the above signal the last class, okay, in the last lecture. So we just used it. I didn't say much about it. So let me just say. So we said that one thing to remember is that if there is a periodic signal x of t, and if I represent in terms of a Fourier series, then this whole series is also in time domain. Okay, you must remember, because unless I cannot use an equality. If at all they are not, the domains of both of them are not same. This is a function of time. This should also be a function of time. Then only this equality holds. So a similar thing should happen here. So if at all I am writing 1 upon Ts summation k equal to minus infinity to infinity delta of f minus k of fs as a Fourier series. So this should also be in frequency domain. So what we wrote was 1 upon T of s summation n equal to minus infinity to infinity Cn. Now here comes the point, j of 2 pi NTSF. So this was the function, this was the series which we wrote. Now why this NTFS? See, one thing to remember is that if I take you to the Fourier series concept, that x of t, let us say it's the periodic signal. So here this was going from this to this, c of n e raised to power j 2 pi f not t, okay, n to n. Or let us say if I try to write this if you remember, it's a j omega naught, or should I j n omega naught. So this is what we remember from signals and systems, where omega naught was nothing but 2 pi by t naught. T naught was the period of the signal. Okay? Period of signal. Or this can be equivalent written as 2 pi f naught. So basically, if we need to write x of t, it's the periodic signal in t, as a summation of complex exponentials. So each of the exponential must be a, let us say, an integer multiple of the period. Let us say the base is j 2 pi f naught t. Suppose if I consider this is what? Cos of 2 pi f naught t plus j times sine of 2 pi f naught. Okay, so this is a cosine signal of frequency f naught, and this is a sine signal of frequency f naught. If I put an n also here, so the n will also come here, and you will have now another. You can have several cosine and sine functions which are now which are having frequencies which are multiple of the fundamental frequency f naught. So the same thing should exist in the frequency domain as well. But now here the problem is that we require complex exponentials which have this property in the frequency. So first let us create this. Okay, let us see that how it is possible. So if I say that e raised to power j n 2 pi by f of s into f, if I say this is a complex exponential in the frequency domain. Now here you will feel this f of s is nothing but this. Okay? So here you will feel that what sort of signal it is. So in order to study this, let us assume what is e raised to a j 2 pi by f of s into f. So you will realize that this complex exponential as a function of f will be having the desired property which we were studying for the time domain complex exponential. Okay. Now this observation you have to do it yourself. This is very simple to think of. For that I have made a base. The base is that you require a complex exponential, let us say, or if I need to explain it further, let us see if this is suppose a sine signal. Okay. This goes to both the sides. So what are these crossings? Okay. If it is standard signal, it will have pi, 2 pi, then 3 pi, then 4 pi, and it goes, because sine is 0 on odd and even multiples of pi. But if I consider sine of 2 pi f naught, okay, if the frequency is f naught, it means this many number of cycles in a second. So you will have these crossings in terms of f naught, okay, or in terms of 2 pi by t naught, these crossing points. Similarly, it should happen in this. So the crossing points should be in terms of now f of s. So that is why the complex exponentials which we used in the last lecture, let us say we were deriving this, so we said that this can be written as a series. Here is 2 pi n. TSF. Why? Because TS is nothing but 1 upon f of s. So this is what I wanted to say about the last lecture. Yeah, one more thing. So this is, I think, should be clear once you try doing it. If at all this is not, then we can discuss it. Okay. With those who are experiencing difficulty in understanding this, or if at all you have a better explanation, then you are most welcome. Sometime in another lecture, in the next lecture, you can take over and explain it to your classmates that yes, a better explanation exists and this is the way we can study this. Means we require exponentials, let us say here. Now our sine wave is like this. The axis is f-axis, okay? And these crossings should come in terms of f of s. These should be functions of f of s. Okay. So this analogy you have to draw from the time domain. I told you that this axis was time, and this crossing come in terms of t naught. A similar thing should happen here. Now the fourth thing. So this is what was there, I think, pending. So the last thing which is pending from the last lecture is that the natural sampling, the circuit. The circuit for natural sampling. See, why we are discussing the circuit is that this is very easy to understand. This clarifies our concept, and this is given in the textbook at least. Why we are religiously following a few textbooks? Because this is a large class, and it's better if at all you have a ready reference from where you can study it. Circuit for natural sampling. So this is a representative circuit. Representative, not exact. Means you have to make it through components. The logic is simple that this is W of t. This is going inside, and this is, let us say, you can say that this is the earth terminal. Okay. Suppose this is the switch. Okay. And this is terminal. This is the output. Output is simply WST sampled signal, or the instant naturally sampled signal, which is WT into S of t. Okay. This is an analog switch, and it's controlled, or its on and off is controlled through a clock signal. Okay. We represent this clock signal as S of t. So this is a representative circuit. This is an analog switch. So generally, you will find that this natural sampling is done in hardware like this. That you will have a clock type of a signal which will control the opening and the closing of a switch. And this switch, if closed, will give the output that part of WT, and if it's open, then you will get 0 because of this earth terminal. You will get 0. So you will get a signal which takes the shape of the analog waveform. Okay? I think this I just told you in the last class that how this happens, but I didn't draw the circuit, a representative circuit. Yeah, and the fifth order. Sorry, I forgot one thing. That last time we said that we can create an equalizer which has a response like 1 h of f. In our case, your h of f was a sinc function. Okay. In our case, that is instantaneous sampling. Instantaneous sampling with I think you can call it as a select function. Standard rect function. I think this is rect function. H of f was is a Sync function. Okay. I am not writing the arguments. Let me just clear it like this. Is a, let us say this is your sync. This is okay. It means it will have some arguments inside and we multiply. Now the problem with 1 upon HF is that if you know, I think you know already that same function has this sort of a shape and this goes on. What will happen at the 0 points? See, this is the 0 point. If at all you draw or if you try to make 1 upon h of f, this 1 upon h of f goes to infinity at 0 points. Okay, goes to infinity at 0 crossings of h of f. You can say infinity or you can say it becomes undefined as well. Means what value it will take. It is having very high value, or 1 upon 0 you can say is not defined. Infinity as a number doesn't exist. So then our statement is falling flat. See, we wrote it. Here. So low pass filtering, but there is high frequency loss in the recovered analog waveform due to the filtering effect. Okay, we see that this shape, the shape of the our baseband spectrum changes because of this h of f. So we said the loss can be reduced by decreasing tau. Okay, this I gave as a homework, or using an equalizer with transfer function 1 upon h of f. So this is the conclusion now. That since h of f is a same function, it has 0 crossings. So what will happen at the 0 crossings of h of f? So you can clearly see that this is not the case. This sync function, if at all our sampling rate is good enough, this whole sync function is having multiple copies of the analog waveform spectrum. So we will have 1 upon h of f only for this region. Okay, it means that we will only take values of the main lobe. Okay, we take the values of h of f for this region. Okay, and we will design a filter which has 1 upon h of f as the response in this range. So this is a rough explanation of the design of 1 upon h of f. It is not straightforwardly taking the same function from minus infinity to infinity and finding 1 upon h of f, which is not possible. See, if same function has reduced something to 0, you cannot recover it back. Once you do not know anything about the center. See, if I tell you that a into 0 is 0, okay, I give you 0. I give you 0 and do not tell me anything about and do not tell anything about A. You cannot recover it. Okay? This is a fact. You cannot recover it. Why? Because 0 reduces everything to 0. If I multiply anything with 0, it is 0. So if I try to recover anything from 0, it has infinite choices. Okay? So you cannot come to a conclusion that what was being initially multiplied with 0. So hence, if sync filter has reduced something to 0, you can clearly see. Let us say if it has reduced this to 0, both sides, then I cannot recover back what was. So that's why assuming 1 upon h of f for minus infinity to infinity is not what we do. We only take this region where our signal gets distorted, and we know there will be multiple copies of the baseband spectrum in the main lobe of the sync function. So we will only take this region, we will create 1 upon sync function in this region, and then we use it as an equalizer. So in our course, I don't think that we have equalizer design as one of the modules. Otherwise, this is a big area, and if anyone is interested, you can see Prof's book and other books as well. Maybe in signal processing, there you will find this equalizer design. Okay, then. So let us now move ahead with. So with PAM signal at our disposal, PAM signal at our disposal, why don't we directly transmit it? I do not. We directly, because this is also a type of a digital signal. Okay. It has some sort of finiteness. It is taking maybe not a continuum of values, but a few discrete values it is taking. So why don't we directly transmit it? Okay, or why don't we directly transmit it? So this is the question. So let me write it down. The reason that it requires a very wide frequency. It requires a very wide frequency response because of narrow pulse width. Okay, let me show you what is that. So if we go back to our previous lecture, so we'll find out if we see such wide spectrum. Initially, the baseband spectrum or the analog signal which we are sampling, let us say, is only contained in minus B to B. But the sampled signal now lies from minus infinity to infinity, and even if we consider the main lobe, so the main lobe is quite wide. The reason being that your pulse which you use in the sampling procedure, let us say h of t which you use, the tau is generally very small. Okay? Why? Because if it is not small, then you cannot sample the signal effectively. Because of tau being small, your sync function is very wide. This is the case of instantaneous sampling, and the same is observed for the case of natural sampling as well. So you will see that such wide spectrum. So initially the signal was from minus B to B, now it is taking a big spectrum. So this is a problem. So if at all I need a wideband channel. Wideband channel means that a channel which easily passes such a big spectrum. So there are two constraints. One is that such a channel may not be economically viable. मतलब ऐसा मिलेगा नहीं आपको. इतना बड़ा spectrum is not available, or it is at such a price that the economics is disturbed. Okay, you are spending too much of money sending just a signal which is not very important, or you could have accommodated more people to earn more money or to offset the cost of the spectrum. Second reason is that such a channel should exist, because you must know that if at all you are moving in a high-speed train or you are sitting in a car, so you will find that sometimes the voice breaks and several different things happen to mobile communication, or you will observe in your home that if you are moving, the Wi-Fi signal strength just fluctuates. So the channel itself is variant, that it cannot pass such a big spectrum without distortions. Okay, so these are the cases. Bandwidth required is much larger. Is much larger than that of the original. Analog signal. Okay. So you have already seen this. So minus B से B तक analog signal था आपका. Suppose it was the spectrum of analog signal was majorly lying from minus B to B, but the sampled signal has a very wide response. It is a very wide coverage. So bandwidth required now to send the sampled signal is now increased as compared to the original analog signal. And noise performance is not better. It's not better than direct analog signal transmission. Okay. Why this is? Because there will be several issues with it. A lot of noise and distortions will add because of the wideband signal. So it may be the case that if you transmit the analog signal by analog modulation, you will get maybe a better error or a lower error than this. It means कि PAM को अगर आप ट्रांसफर करेंगे. So question ये उठता है कि PAM हम क्यों स्टडी करते हैं? PAM हम इसलिए स्टडी करते हैं because now this PAM signal will help us to generate the PCM signal, which really exploits the digital communication benefits. Okay, so we will see. The next topic is PCM only. So let me write it down that PAM is not good. PAM not good for long range transmission, but is useful. But is useful in converting an analog signal to PCM signal. Okay, so we will now go to study the, I think, the last part of module 1, that is the PCM and DPCM. So these are the two topics at which our module 1 terminates. Okay, so maybe next 2 lectures we will go through PCM and then we'll start with module 2. So two things to point out here, that there are few statements. Let us say if I have written PAM is not good for long range transmission. Okay, now this long range term comes. Then this noise performance is not better than direct analog signal transmission. So these are written without quantifying. It means we are not telling the reason for it. See, if you are very much interested in knowing the reason, then you need to go back to the days when the research for PAM and such waveforms was at its peak. So people must have noted down the reason in the research articles, or the companies who are designing systems based on these waveforms in their article notes, or in their notes they must have written it down, that what is the problem really they face. But what we can understand is that for us, because right now we are in pure academics, so for us this wideband coverage is one of a good reason to discard this. Okay, the wideband coverage in minus B2B, then the coverage is very high. And secondly, because anyways you are sampling something, the recovery also generates some sort of an error. ऐसा नहीं है कि आप सैंपल करके theoretically तो निकाल ही सकते हैं, theoretically you can have the original signal back. It is not the case because of non-realizability of ideal filters, as well as having impulse sampling is not very practical. So theoretical concept, once it translates to reality, it will give you few issues. So that's why this is one of the reasons that noise performance is not better than direct analog signal transmission. So this is what I am thinking. This should be the case basically. But for further reasons, you need to go and check the articles. For our purpose, it is not required. So I will say that this is not much required at this stage. We just need to know that yes, this is not used because of this. Very simple reason. So now we will start the study of PCM, which is simply pulse mode modulation. Okay, now there is a pulse we know, there is a code and there is a modulation. Okay, modulation we know. So this code generally refers to a binary code. So in order to motivate PCM, so in order to motivate PCM, we need to go back to our first lecture where we were discussing this discrete time, discrete amplitude system. Now the issue with PAM is that PAM has now given us some signal. PAM has given us some signal. PAM has given us a signal which is definitely discrete in time and amplitude, but the problem is the amplitude values still do not belong to a finite set. The problem is this. So let us see this. So what we have done is that if there was some sort of a signal, let us say, so we said that let us say we arbitrarily sample it. So once we sample it through let us say this is the instantaneous sampling. Sorry, this is maybe the impulse sampling. But if at all you consider the two types of PAM, because the two types of PAMs, you will observe that they were just trying to shape this. Let us say if either you get this sort of a thing or you get this sort of shape. They were not doing anything with these values. So let us say if I say that this waveform can take values from, let's say, minus a to maybe plus a, suppose, or you can take minus a1 to a2. So discrete samples can take any value from minus a1 to a. Okay. So that is the problem, that even after sampling and getting a discrete value signal, we are having any sort of number between minus a1 to any real number. You can say that any real number between in this interval, right? Any real number from the above interval. So now we will first study the process of having a finite state. Means the values which this discrete thing can take, the set is finite. Okay, we will do that. That process is called as quantization. Okay. So we will now study first quantization. Once quantization is done, we will just simply close our study of PCM by drawing its circuit. Okay. So in quantization, let me write it down. The existence of a finite number of discrete amplitude levels, discrete amplitude levels is a basic condition of. So I'm just writing it down. Basic condition of pulse code modulation. Okay. Now why? That because of the word code, you want to assign a sort of a binary code, or you can say that you need to assign, let us say, 0011 or 1100 values to these discrete levels. Okay? So you know that if at all I am taking k bits, so at max it can represent 2 raised to power k levels. So the finiteness comes from this issue of assigning code. Okay? So if at all that is the case, so we need to have a finite number of discrete amplitude levels to which we will be assigning codes. So the existence of a finite number of discrete amplitude levels is a basic condition of pulse code modulation. Okay? So now we will do the study of quantization, and here we are right now studying amplitude quantization. Okay? Amplitude quantization. So process of transforming the sample amplitude m of nts of a message signal mt at t equal to ts into a discrete amplitude v of nts. Okay. Now we call the discrete amplitude which we assign let me write it down and discuss. Taken from a finite sample, taken from a finite set, taken from a finite set of possible amplitudes. So this is the process of amplitude quantization. So I've just written the definition for those who are only reading from notes. So they must know that what we are doing. So once we have this sample signal, we have these discrete values. So now we want to convert these discrete values to values which are drawn from a finite set. Okay. So this process, because this is amplitude, so this process refers, this called as amplitude quantization. So we want to do this process of transforming the sample amplitude m of nts of a message signal mt at t equal to nts into a discrete amplitude taken from a finite set of possible amplitudes. Okay. Now this process of doing this, so we assume, so assumption, right now for our study, assumption for our study right now. This process, the above process is memoryless and instantaneous. Okay, this should be known. Memoryless and instantaneous. Okay. Now, what is the meaning of these two terms? That let us say if you have a discrete set of values which are coming. Okay. So what this is the sequence which is coming to the quantizer. So if at all this needs to quantize this value, so it will do it instantaneously and memorylessly. It means that if while quantizing this is not considering what the past values were or what the future values are. Okay, so this has to be memoryless. I think this you studied in signals and systems, a memoryless system. So that is the same term used here, that the system, this quantizer right now has no memory. Although quantizers with memories are quite effective and they are generally studied in a separate course on source coding. Okay, so our course is digital communication. Here we assume that we know some source coding. So if we know some source coding, so that suffices for us to understand digital communication. But yes, quantizers with memory are always there. Instantaneous means that there is no delay in the system. So once this comes, this is instantaneously quantized, and this quantization is not dependent on the previous or the past, the previous or the future discrete values. So this is sometimes called as, scalar quantization. Scalar quantization. So let us see it through an example. That's what we want to do. Suppose, let me draw it. Suppose our quantizer takes the input, let us say minus MP, and MP is the limit in which our quantizer operates. That is, it takes signals which lie from minus MP to NP. If at all there is a signal which has an amplitude which is greater than MP or below minus MP, then it is clipped up or chopped off. Okay. So if at all your signal exceeds, so if the signal exceeds NP or minus MP, if input signal, if the input signal exceeds MP slash minus MP, it is clipped. Okay, it is clipped, or that part is chopped off. Okay. So assume that, let us say this is, suppose I am, so these are the quantization levels. that the allowed quantization. Quantization. And the width of this is twice of MP upon L. If L is the total number of quantization levels. Okay. So L is the total number of quantization levels. So obviously, once L is the total quantization level, so you are dividing minus MP to MP, so twice of MP is the full range, and you are dividing into L. So the width of each of the interval will be twice of MP by L. So if at all this is what is happening, so suppose I am drawing the quantization levels. I think this quantization you all must be knowing, but for the sake of completion, I am going in a very general or very basic sense. Okay? So you suppose these are the quantization levels, and this is suppose, let us say this is the discrete sample which comes. So this sample lies in between these two levels. So there are two ways. So I can say that if at all my sample lies in between the two levels, so either I can say that it takes the value above or it takes the value below. Okay. So I simply assign the below value or the above value. One more thing which is generally done is that if a point lies in between, then I assign the midpoint of the interval as its value. Okay. So this you will do for the full waveform. So this is what the discrete samples you are getting. So you will see that this is what the way quantizer works. So for an input discrete sequence, it will for each sample it will see that in which interval it lies. So if that interval is identified, so the midpoint of that interval is assigned to it. It means now that discrete sample will take the value which is given by the midpoint of the interval in which it lies. So this is a simple quantization process. Okay. I started. So in this, if for quantization, choose the midpoint of the interval in quantization. In quantization above, choose the midpoint of the So let us now study a few terms. With regard to this process. So if at all this is a straight line, this is your m of k minus 1, this is your m of k, this is your m of k plus 1, this is m of k plus 2. Okay. And suppose this is your v of k. V of k. So this is called as a partition cell. Okay. This is called as a decision levels for all k, obviously for all k. These are decision levels or thresholds, or decision thresholds. Okay. And what is V of k? So V of k are called as representation levels. representation levels or reconstruction levels. Okay. It simply means that if at all the discrete value, the input, let us say if the input value falls in between mk and mk plus 1, so you will be assigning the value v of k to it. Simply that is the meaning. And the spacing between, so this terminology is important to know, because once we have gone through the study of quantizers or quantization process, we need to know this. Otherwise, if anybody questions us that, let us say, if you have studied quantization, you must be knowing that what is representation levels. So despite being knowing what quantization is, you cannot tell what is representation. So some sort of a theory we should do. The spacing between two adjacent representation levels, is called a quantum or step size. Okay. In few books, you will find that this is written as quantile or something. Okay. So that is, I think, there is no uniform notation, I feel, because a few textbooks says quantile, a few says quantum or step size, but we must know that there is a proper name, and this name comes from the logic through which we are designing these quantizers. Okay. Next. So K, I think I have not yet said, so K belongs to 1, 2, 3, and this goes up to L. L is the total number of amplitude levels used. Okay, so L is the total number of amplitude levels used. In quantizer, okay. I have not yet mentioned. Okay. I need to mention one thing, that all amplitudes in suppose we are taking m of k inside, m of k plus 1, we are leaving it for the, so this close bracket means that if the discrete sample takes value mk, so it will be assigned the value v of k. But if it takes a value m of k plus 1, then it will be assigned a value v of k plus 1. It means mk lies, we are taking mk with us, mk plus 1 we are leaving it for the next representation level, are represented by v of. So this is pretty much what we are basically doing in quantization right now. That is, for our study of PCM, this sort of a quantizer design is appropriate, and this works for us. And in most of the quantizers, we will doing something related. So you need to choose levels. So we have chosen some levels in a way that we have chosen them as midpoint of the intervals. So we have defined these intervals. They are uniformly spaced. So one important construction thing which we have used here is that they are uniformly spaced right now. So this distance is same. So our partition cells are of same size. So if at all my sample lies in a particular partition cell, so if I check, if it is mk, then I will assign v of k, or if it is mk minus 1, then I will assign v of k minus 1. And else, if it lies in this partition cell, I will assign v of k. मीन्स दोनों हमने इसको भी कवर कर लिया है कि अगर कोई डिस्क्रीट सैंपल आपका एग्जैक्ट mk है या mk plus 1 है या mk plus 2 है तो क्या करेंगे, बिकॉज ये एक क्वेश्चन है माइंड में. इफ एट ऑल यू आर स्टडिंग और गोइंग थ्रू क्वांटाइजेशन फॉर द फर्स्ट टाइम, यू माइट थिंक that what happens if the discrete value is exactly mk or mk plus 1 or mk minus 1, whatever, because we are saying all this for all k, so you must remember that. Whatever we have written is for all k. Otherwise, this is a big mistake which generally a few of us do, that we assume that only this k is there, but it should be known that this k takes values from 1 to L, and whatever we have written is valid for all those capital L values. So pictorially, this can be represented like this. So there is a quantizer, okay, which is a sort of a mapping. You can say, I'm not calling it the function. This is the mapping because discrete sample, V, and let us say the input is continuous sample M. Okay. This mapping V is equal to Gm is a quantizer characteristic. Okay, quantizer characteristic. So this is the term used for it. The characteristic, which is a staircase function by definition. Okay, which is a staircase function by definition. Now, why the staircase function? You may realize, I will draw it. I think in next lecture I will draw this. But because of this property, it is a staircase function. Because anything which lies between mk to mk plus 1 is given a constant value v of k. So if at all I try to, let us say, draw the characteristic. So if at all my input signal lies on the x-axis, so I have divided them into, let us say, these partition cells. And if suppose this is my output, so if at all this is your m of k and this is your m of k plus 1, so anything lying in between will be given a particular value, that is v of k. So this is suppose v of k. So for this for mk plus 1 and mk plus 2, so anything is like this, so I am assigning a value which is suppose v of k plus 1. This is v of k plus 1. So this you will realize that this goes with both the sides, so this is the staircase function. We will study it in deep in the next lecture. So right now I will just write one thing and then we'll close. So quantizers are of two types. Right now, it means for us, suffices to know that there are two types. One is uniform and one is non-uniform. Uniform and non-uniform. We will use both types. Okay? That's why I'm saying that right now for us it suffices to categorize them into these two parts only. That is, one is uniform and that is non-uniform. Okay. So I think we are done for today, and we'll discuss the quantization, noise, and the misthread and mid-rise type of quantizers on Friday. And in another 2-3 lectures, we will be done with the first one. Okay. And then we'll immediately start with the second one. So we are done for today. So those who want to stay back and talk, they can. Others can quit. And they may get ready for the next lecture.